Okay, so in this video we're going to take a look at a concept called superposition. Now this isn't just a concept that is applied in circuit analysis, but it's applied in many fields of engineering, mathematics, and physics in general. It's that when you have a large thing that is composed of a bunch of smaller things, you can consider that large thing to be the sum of a bunch of smaller things. So let's take a circuit, for example. Let's say I have a circuit as follows. And let's say I have this voltage source here, and let's say I have another voltage source here, and let's say I have another voltage source here, and let's say this is VA, and this is VB, and this is VC, and this is VD, and I'll call this RA, RB, and RC, and RD. Now imagine I'm interested in this voltage, let's call this Vx. So pretty much superposition says that Vx will have some sort of dependence. I mean, this is pretty intuitive if you look at it. I mean, it'll depend on VA, VB, VC, and VD in some regard based on the ratios of these circuit elements here, RA, RB, RC, and RD. So now, when you actually have a circuit, and in terms of let's just think of a simple voltage divider here. Let's call this plus 5 volts, let's say, and this is minus 5 volts, and I'll call this RA, or let's call this R1 so we don't confuse and think it's something special, and let's call this one R2. And let's say that this is my voltage now that I'm interested in, and I'll call it V1. So now how do we find V1? So superposition says that if I take this circuit, so let's take a look at this circuit now because this one's a little more interesting than the first one. So pretty much I can decompose this single circuit into two circuits where I consider the contribution of each source independently. So what I'm going to call is, let's say I'll call this one V1, let's call it V1 plus, because it'll have to do with the plus 5 volt. Now notice these resistors will stay the same, and I can say that this is actually the summation of two circuits, that if I had these two circuits and they were connected as follows, would give me the exact same circuit as I have in my case. So then we'll call you V1 minus. And so this is R1 and this is R2. So then what I say is that V1 actually is going to equal V1 plus V1 minus. That is, the total voltage found at this node with respect to ground will equal the voltage that is contributed by this positive across these two resistors, and the sum of that voltage as well as the sum of the voltage that is found when contributed, or when only the minus 5 volt source is contributing to that. So what would that actually look like? Let's just do it in terms of variables here. So I would have V1 plus would be a voltage division. It would be 5 times R2 divided by R1 plus R2. And note that I will highlight this just to give it a sort of corresponding where it's coming from. And so this is basic voltage division. We've already looked at voltage division in a previous video, so if you're not sure about that, have a look. I will link that below at the end of this video. And so what we have now as V1 minus will be the contribution due to this minus 5 voltage source. And so what is that going to be? That's going to be minus 5 times, now notice this voltage division is going in the opposite direction. So this one was actually V1 plus depends on R2. But notice that if my source is down here, V1 plus actually depends on R1 in the numerator. So this will now be R1 divided by R1 plus R2. So you get the idea. I mean, it's essentially I look at each thing individually and then I can add the two results together. So if I were to add this, well, let's just stay consistent with this first. So this is going to be this blue one is going to correspond to this term here. So you can see which term actually contribute, or which actually comes from where. So now what happens? This is going to be 5R2 minus 5R1, and this will be over R1 plus R2. Now notice this is an example. These numbers 5 in general can be anything. They don't have to be positive and negative. They don't have to be both positive. They don't have to be both negative. They can be anything. But this is a simple example that is a very practical example, which you would expect to deal with in a lot of cases. So we're using this as a starting point for superposition. So this is a sort of general concept. So let's take a look at a quick example in which we can deal with both AC and DC circuits, because not only can we deal with positive and negative circuit or voltages, we can deal with AC and DC circuits, and we can superimpose the AC circuit with the DC circuit and find everything individually and then add everything together at the end. So let's take a look at the following circuit, and it is a relatively simple circuit, but it is the combination of two types of voltages nonetheless, so it is a useful example. And so here I'm going to call this VO, and notice it will be with respect to ground, so it'll be plus minus there. I'm going to call this thing plus 5 volts and this thing minus 5 volts. This here is going to be Vs, and it's going to equal 10 sine omega t. Now the frequency isn't important, so we're leaving it as omega. This is going to be a 5K resistor, this here is a 10K resistor, this is 15K, and this is 27K. Okay, so how do I deal with this type of circuit? So first what I'm going to say is let's look at AC sources only. So if I have AC sources only, what do? I must get rid of my DC sources. How do I get rid of my DC sources? So let's just make a note here. So when turning off sources, voltage sources are short-circuited and current sources are open-circuited. Now what do I mean by that? I mean, if I have a voltage source, replace that voltage source with a short circuit, so just replace it with a wire. If I have a current source, just open that current source. So where that current source would have been, there is now a gap. And so this type of thing is implied whenever we're trying to look for superposition due to multiple sources. So if I want AC sources only, then what I will do is I will short my DC sources. Okay, so now let's redraw that circuit and what it will actually look like. So I will have here, well, we don't need to do that. We'll have a resistor here. I'll have a resistor here. This will be ground now. This will also be ground now. Notice that they are shorted to ground. And I will have this resistor here with respect to ground. So this is 27K. This is going to be 15K. This is going to be 10K. This is going to be 5K. And this is still Vs. And now what I'm going to do is I'm going to call this VOAC. Okay, and this is just to denote that, this is the AC component of the voltage. And so what is VOAC actually going to be? If I think about it, all three of these resistors are actually in parallel. And that parallel combination of these three resistors is in series with this one. So essentially I have a voltage divider here. And so the voltage VOAC is going to be the voltage that's divided across this thing, divided by the sum of this thing plus this thing. Okay, and so what does that actually look like in terms of an expression? So we said this is Vs. So I'm going to leave it as Vs for now, and we'll replace it with Vs equals 10 sine omega t after, just to keep the expression a little neat as we deal with these parallel combinations. So this is going to be 10 in parallel with 15 in parallel with 27. And all of this is going to be divided by 10 in parallel with 15 in parallel with 27 plus 5K. And so if I take the parallel combination of the top, I will find this is Vs times 4.91. Since that is 4.91, if I add 5 to that, I get 9.91. And so then VOAC is actually equal to Vs times 0.495. In other words, VOAC equals 4.95 sine omega t. And so this now is my AC component of my signal that appears at the output. Now this is only one of the outputs, notice, or the voltage sources. There are 3 in this entire question. And so now we have to consider the DC sources only. So I'm going to short the AC sources and look only at my DC circuit. So let's look at DC sources only. And so I'm going to short AC source. And I'll write source because there's only one of them. And so if I short my AC source to ground, this I replace with a short. This resistor is still there, so is this one. And you'll notice that these two voltage sources are turned on at this point. And so I can call this VODC. This will be plus 5 volts, this will be minus 5 volts. This here is 10K, this is 5K, this is 15K, and this is 27K. Now what I can do is either I can look at it this way and do a simple voltage division if I'm comfortable enough doing that, or what I can do is I can realize that this circuit can further be broken down into 2 sub-circuits. So I can consider the positive. So let's say plus 5 volts on. If plus 5 volts is on, what will my circuit look like? My circuit will look like the following. I will have, this is turned off now. So this is now on. And this resistor is still there. And this I can call now, let's call this VODC plus. Okay, this is plus 5 volts. This is 10K. This is 15K. This is 5K, and this is 27K. And I say on the other side that minus 5 volts is on. So now if minus 5 volts is on, that means plus 5 is off. And I will have here this resistor still there, and that's still shorted to ground because I'm considering only my DC circuit. And here I will have VO, let's call this VODC minus. And this is going to be minus 5 volts. And this is going to be 10K, 5K, 15K, 27K. So now, I have 2 circuits that are easy to analyze this way. If you're comfortable analyzing it directly doing this, that's also fine. You can do it that way as well. For those of you who cannot, I would always recommend breaking it down to the simplest case possible and analyzing only that, as long as you're comfortable with it. Once you deal with a lot of these problems, you'll start getting more and more confident in your ability, and you will be able to solve them much faster, and you'll be able to just look at them directly and solve it based on that circuit above, as opposed to actually having to draw every single one of these out. But for the time being, for the purpose of demonstration, we will draw all of these out. So now let's take a look at VODC plus. VODC plus, I see that this 5K and this 15 and 27K are all in parallel because they're all connected here and they're all connected to ground. So VODC plus is simply going to be 5 times 5 in, 5 in parallel with 15 and 27 here. And this whole thing is going to be divided by 5 in parallel with 15 in parallel with 27 plus 10. Okay, so this voltage is going to be divided across these 3 in order to get VODC. And so if I actually do this combination, parallel combination, I'll get this is 5 times 3.29. If that's 3.29 in the numerator, this should be 13.29 in the denominator. And this voltage will be 1.239 volts. And so if I do the exact same thing here with VODC minus is actually going to be minus 5 times this parallel combination. Now notice in this case the parallel combination changes. So I have 5, 10, and 27 across this way. In the other case I had 5, 15, and 27. So I have 5, 10, 27 is being divided across. Well, those three in parallel, and then it's being divided across that one. So I take this parallel combination and I divide by the same parallel combination plus that resistor that is here now, and this is 15. So plus 15. So now if I do this, I will find VODC minus actually is going to be equal to minus 5 times 2.97 divided by 17.97. And so the number I get here is minus 0.826. And this is VODC minus. So now what do we do? Now what I say is that VO is going to equal VOAC plus VODC. And I can say that VOAC plus VODC we say is going to be equal to VODC plus VODC minus. This we found was 4.95 sine omega t. And this we found was 1.239. And this we found was actually 0.826 volts. Now if I take the sum of this, I will get this is 4.95 sine omega t. 1.239 minus 8.26 gives 0.413, and the final answer is obviously in volts. So here you have your final answer for the superposition of two DC sources as well as one AC source. And of course, as we expect, the output voltage is therefore an AC plus DC voltage. So in this, just to recap, I guess, in this video we looked at superposition, which essentially says that if I have multiple sources, I can break down that the circuit that deals with all those sources into sub-circuits, all which consider only one source where all the other ones are turned off. Now how do we turn off the sources? If it's a voltage source, we replace it with a short circuit. If it's a current source, we replace it with an open circuit. Once we can consider one source at a time. We take a look at that source. We find the voltage that we're interested in. So in this case, we were interested in VO. In this case, we call it VOAC because it's only the AC component. So we find VOAC when it only depends on one source. Now I look at the DC sources. So I find VODC when it depends on these two sources. Now in this case, I figured I'd make it even easier by considering two sub-sub-circuits. And so these sub-sub-circuits have single voltage sources, and we basically did voltage division across both of these, added the results together, added that to our result that we got from the AC component, and we have our final AC plus DC voltage here. So I hope you found this video helpful. If you haven't already, hit that subscribe button so you can have notifications as soon as we do upload more videos in the future. And other than that, I want to thank you guys for watching. Have a great one, and we'll see you in the next one.